first thing we're going to look at, this is pretty easy. We didn't quite get to it before. Alkynes. So we talked about alkanes, we talked about alkenes, and now we can do alkynes, where we put a Y in there. Any idea what that's going to be? Yeah, triple bonds. We don't have a whole lot to say about these because they really work the same way or very similarly to the double bonds, to the alkenes. So if you were to look at this molecule, what do you think it would be named? How do you think it would be named? You had to guess. I'm confident you can figure this out. What would it be if it were a double bond? Close. Yeah, there's two carbons, right? So if there were a double bond there, it would be ethyne. Eth is 2. Yeah, so it'd be ethyne, right? And just because this is a relatively important molecule in the world, it is more commonly known by its common name, which is acetylene. But it's the same thing. But if you were to name it properly using the rules, it would be ethyne. One interesting thing about triple bonds is they're linear, they're straight, they're not bent. So if we look at the bond angles around here, that's actually 180 degrees. We weren't just writing it kind of straight to make it easier like we do sometimes. So that means that when we write line or skeletal structures of alkynes, we don't make the zigzags. We don't bend things. So if we wanted to make like hexyne, for instance, you would go 1, 2, 3, and there's 4, so 3 hexyne, 5, 6. And that would be 3 hexyne. If we numbered those, 1, 2, 3, 4, 6. So you keep it going straight instead of taking another zigzag because of the linear bond there. And that would be the same thing if it's up at the beginning of the chain too. So you could do like so this would be 1 hexyne. And either side of that triple bond is a carbon. But we don't make the angle bend right around those. That's pretty much all we have to say about triple bonds, about alkynes. All the other stuff holds the same with alkenes. So the naming, the numbering, all that kind of thing is all the same. There's really nothing else we need to do there. Substituents can be on other parts of the chain, but the carbons that are part of the triple bond can't have substituents because they already have their 4 bonds. So they'll only be whenever, well, I guess unless it's up at the beginning here, but generally the substituents will just be elsewhere on the chain. Okay, so that's alkynes. Another class of reactions, or of, well, let's talk about the alkene reactions. One of the things that's so useful about alkenes is that unlike alkanes, they are reactive. They can react with other kinds of molecules and start to help you build the kinds of things that you might want to design if you're designing a new molecule. So the ones we're going to look at fall into this category of alkene addition reactions. The organic chemistry term is addition reactions, but you can also think of them using the term that we've used before, which is composition or combination. So you're going to take your alkene, add something else to it, and then make one product. We're going to look at two ways that this works. The first one's called hydrogenation. Which means we're going to add hydrogen, H2, to an alkene. And that reaction looks like this. So let's take just like a nice small ethyne. We're going to add hydrogen to it. And I'm going to use a different color so we can see what's happening. When a molecule like that reacts with hydrogen gas, actually nothing happens. It needs a catalyst, something to help it along. And the common catalysts that are used here are some different metals from kind of the middle of the periodic table. So you'll see some different metal catalysts like nickel, or sometimes palladium or platinum, depending on what type of molecule needs to be hydrogenated and how exactly it's working. You'll see those different molecules used. Those are catalysts. If you remember back when we talked about catalysts, so the reaction between an alkene and hydrogen has a really high activation energy, meaning it's not just going to happen all on its own. When you add the catalyst, that lowers the activation energy such that it can actually proceed. So we want to add those things together. In order to add anything to that alkene, we need to get rid of the double bond, because otherwise those carbons would have too many bonds. So the product will not have a double bond. And the hydrogens will be added one on each carbon where that double bond was. So H2 is like H, right? And each one H is going to go to each carbon. So think about the molecule we made. What's the name of that? Ethane, yeah. So we started with ethene, an alkene, and we produced ethane, an alkane. So hydrogenation, adding hydrogens, changes the functionality of the molecule from having the double bond to not. And when we see this in line structures, it actually makes this drawing products of a reaction like this pretty simple, because it just looks like the double bond is going away. If we took, let's say, cyclohexene, and we hydrogenated this with a nickel catalyst, the product would just be cyclohexane. So it looks like something's disappearing in this reaction, but nothing's disappearing. Actually, hydrogen is being added. But in adding hydrogen, we no longer have a double bond. So that's why I can kind of look that way. The other interesting thing about hydrogenation is it's often non-selective, meaning that if you had a molecule with multiple double bonds, you can't really pick to just hydrogenate one or the other. So everything in the molecule gets hydrogenated at once. And you can think of that as just getting rid of all the double and triple bonds. And they don't talk about it in your book, but you can also hydrogenate triple bonds, alkynes. It does the same thing. Brings them all the way down to single bonds. There are ways to stop at the double bond, so just hydrogenate them once, but we won't go into that. You'll learn that if you go on and take some organic chemistry. So that's hydrogenation. The second and last reaction we're going to look at, addition reaction, is called hydration. What do you think we're adding here? Water, yeah. The water adds in much the same way that hydrogen did. If we take that same ethyne to start, we're going to add water. Now, I'm going to draw the water a little bit strangely. I'm going to draw it as HOH, kind of like when we thought of it as an acid base, HOH. The reason to do that is so that we think about it the same way as hydrogen. Excuse me. So hydrogen was H2, HH. Water is HOH, which means it's going to add in much the same way. Again, this doesn't usually proceed on its own. It needs some kind of a catalyst, and one type of catalyst that you'll see is acid. Sometimes it's written H+, sometimes it's written hydronium. And that's just showing that we have to do this in acid to get it to proceed. There are some other catalysts, other ways to do this too, but this is a common one. So once again, we keep the whole molecule that we started with, but we want to add these new parts to it. So we're going to add the H to one side and the OH to the other. We no longer have the double bond because carbon has to have more things connected now. And this is now a new type of what we call a functional group, which we'll talk about in a little bit. A new kind of part of the molecule that's going to influence the way that it reacts. In this case, it's the OH. An OH group on a molecule is called an alcohol. So this molecule is now ethanol. When we translate this to the line or skeletal structure, it also kind of a little bit obscures what's happening. So we'll start with that cyclohexene again. We would draw this product. So what it looks like is that the double bond is, you're losing the double bond and you're adding OH. And that's true, but you're also adding H. So there's also a hydrogen over on this carbon, the other carbon of the double bond. See, there would have just been one hydrogen there, and now there's two. So don't forget that when you're adding these, you're adding both the OH and the H. You're adding the entire water molecule, even though we don't show the H's in the line structure, so sometimes it's hard to see. All right. One other kind of unusual or thing that we have to deal with is that the HOH, the water molecule, is not symmetrical like HH. So in some structures, that's going to make a big difference in what the product's going to be. So let's take a look at propene, which is this. We could also draw it like this. If we do the same titration reaction or hydration reaction with this structure now, there are two possible products, because we can either go HOH left to right, or we can go HOH right to left. So let's draw those. We lose the double bond, and we add H and OH. There's one possible product. Oops. And here's the other one. If we draw those out in line structures, this one would look like this. And that one like this, since we don't draw the hydrogens. What's the difference in those two structures? Are they in fact different? Or are they the same? Well, or are they isomers? They all have the same parts. They have the same carbons, hydrogens, and oxygens. But are they connected in a different way or not? What do you think? Connected in a different way or the same way? They look different? Yeah, they're different. In this case, the OH is coming off of the end of carbon number 1, and this one it's number 2. So if we were to name this like a substituent, this would be 1 whatever, and this would be 2 whatever. So those are isomers. So we have to figure out actually which is correct, or which is the major product. In this reaction, both of these will form, but the biggest product will be this one. And so we would call this most favored product, or the favored product, or the major product. And the other one would be the minor product. All right, so how do we then predict what's going to be the most favored product when this reaction happens? The rule is, you can think about it two ways. Some people like it one way, some people like it the other way. So one way you can think about it is, the OH always goes to the carbon that's connected to the most other carbons. You see how this kind of goes in the middle rather than on the outside, where the carbon, so this carbon's only connected to 1, whereas this one's connected to 2. That's one way to think about it. The other way to think about it is, the hydrogen goes on the carbon with the most other hydrogens. So the hydrogen goes to the C with the 2 H's, not the C with the 1 H. So whether you want to think about it as where the OH goes or where the H goes, doesn't matter, it's the same thing, but make sure you have one of those that you're thinking of so that you can draw the correct product. All right, let's try it. See if you can draw the product of that reaction. Remember, Getting rid of the double bond, you're going to put the OH, but you have to determine which carbon it's going to go to. So did you get this one?
So it just removes the double bond and keeps it.
Yeah, right, because that's not going anywhere. I mean, we don't take anything off of the original, any atoms off of the original molecule. We're just losing the double bond. Okay, let's try another one. What do you get for the product of that one?
So you're basically taking that double bond and just adding it outside to where the most substituents are.
Mm-hmm.
I just noticed that comes up notes.
Yeah. Yeah. So for this one, you just put the OH here, right? Yeah.
My notes have it in the middle.
You mean like here?
No, down there.
Here?
No, one more.
This one?
Yeah.
From the double bond starting over here?
Oh.
Let me see, maybe there's a problem.
Unless that's a different one. Don't look in aligning to me.
Yeah. Sorry. Yeah, so you see the structure there? The OH has to go on one of the two carbons from the double bond. So either the left or the right, one of the two carbons, because that's where it's connecting. It's adding across the double bond. So the H to one side of the double bond, the OH to the other side of the double bond. Well, sort of. This is the major product. The major product is not where we would put it on the end. So that would not be the major product. That would be the minor product. Because the OH goes to the carbon with the most other carbons attached. All right? Yeah. Okay, so that's alkene reactions. There's way, way more of these. Not in this book, but if you want to take organic chemistry, the alkene reactions will be a big part of that. We don't need to go through more of that right now. All right, another important class of compounds are called aromatic compounds. Now, it sounds like these compounds are named that because of a smell, because that's what it means. And that is kind of where they come from, but that's not what they mean in organic chemistry. So here's what we mean by aromatic compounds. We're talking about a very specific compound, type of compounds that have this ring structure, but not just the ring structure. They also have alternating double bonds within the ring. The most common aromatic compound is something called benzene. Which is kind of like cyclohexane, but then with double bonds alternating throughout the ring. Like that. The reason that it's so special, and one of the things about benzene is there's actually two ways you can write it that are technically isomers, but, well, they aren't. They're called resonance forms, but they look like isomers, but they're actually equivalent forms. So we could have drawn the double bonds on the other side between different carbons, and we get the same structure. And because of that, there's a symmetry. When we look at the actual structure, like in real life of this molecule, we don't see alternating double and single bonds. We see this kind of average all the way around the ring where it's all the same. So often benzene is written not with the individual double bonds like that, but with a circle in the middle. And that indicates this kind of averaging of the different types of the different double bonds around the molecule. Because of this, because it can do this, it is especially stable. And because it's especially stable, it is that type of a structural piece is present in all kinds of different molecules. Biological molecules, things in nature, things in like graphite structure is similar to this, and that's a mineral. So all kinds of areas of nature see this structure. So it has its own rich chemistry. One example is of this being stable is benzene doesn't do the standard reactions of double bonds that we just saw. So the hydration, the hydrogenation, benzene doesn't do that. You need some special extra strong catalysts to get it to work. And that's because it's so especially stable. One issue with that then is that it becomes often a problem molecule, like a problem in nature, a pollutant, a carcinogen. You know what carcinogen means? We know that word? Yeah, it means something that can cause cancer. So benzene-type molecules and things like benzene, so this molecule is known as biphenyl. There's molecules where it's like benzene's kind of mushed together almost in a honeycomb type arrangement like this. And there's pictures in your book of even these bigger ones, these polycyclic aromatic hydrocarbons. If you hear about these various types of not great molecules, whether they're, you've heard of PCBs. PCBs are polychlorinated biphenyls, so molecules like that one on the left with chlorines all around them. And this was a really common plastic additive, a dye that was used in a lot of plastics for a long time and ended up being a really, really bad pollutant. They're banned now, but they're still in nature, and they're still one of the reasons that you can't eat fish from certain freshwater sources, or that you're not supposed to eat a lot of predatory fish like tuna, those kinds of things. It can be partially it's metals like lead and mercury, but also part of it is these types of benzene structures. These are also products of combustion. So anytime you're burning something, we know combustion products are carbon dioxide and water, but that's only if it burns perfectly in an excess of oxygen. Most things that burn don't actually have enough oxygen to burn fully. And so they end up making these kinds of molecules, which are kind of some of the black stuff that you see when you burn things. And one of the reasons why it elevates your cancer risk to get burned stuff in your body, whether that is smoking, which has less to do really with things like additives and chemicals that are added to the cigarette, and it's more just anytime you're burning something, if you then get that burned stuff in your body, you're exposing yourself to carcinogens. Same thing with like grilled meats or smoked foods, things like that. You're also getting those sorts of combustion products. It doesn't even have to be meats. It could be grilled vegetables, anything that has those delicious, black grill marks and things on them. Yeah. So, which is not to say like avoid all of that stuff all the time. It's just, right, there are molecules there that can elevate your risk. Okay, so that's aromatic compounds. Now we're going to put this all together in make a list of what we call the functional groups, and this will be the last new thing we do for the semester. Functional groups are the things that make the molecules work. We talked about how alkanes are really unreactive. They don't do a lot of stuff. Brett, you did that in lab last week or 2 weeks ago, where you mixed stuff, like tried to mix the chromic acid and other things with alkanes. They didn't do anything unless they had things like double bonds or OH groups. So the functional groups are the things that are on molecules that actually cause them to be reactive and cause them to do transformative things. We're going to make a little list of them. This isn't exactly in the book. It is in the book, but it's kind of split among chapters, and we're not going to go through the details of everything, so we're just going to put them together in a list, and then we're going to practice identifying these in molecules. So for each of these, we're going to say the name of the functional group, what it is, the structure, and then we'll give an example of a molecule that has that in it. All right, so our first functional group is one that we already know, the alkenes. So an alkene is going to be like this, right? Double bond. And we could draw a molecule that has a double bond in it. So what that tells us is that molecule is kind of defined by its double bond. The double bond is what's going to go out and react and do things, maybe some of those reactions that we just learned. And that's what makes it the functional group, the thing that functions on the molecule. All right, then we can look at alkynes. That's our triple bond. The other ones we just learned, the aromatic functional group. So something that contains benzene. Sometimes it's written with those 3 double bonds, and sometimes not. Sometimes it's written with a circle. That molecule, by the way, is toluene. It's a common solvent. Like if you ever smelled model glue, either by accident or on purpose, that's toluene. Now we'll get into some non-carbon non-carbon functional groups. We mentioned this one earlier. The alcohol functional group is when you have an OH attached to something. Something like that, that's isopropyl alcohol or isopropanol rubbing alcohol. Similar to an alcohol, but with a nitrogen instead of an oxygen, is called an amine. And that can either be connected to hydrogens or other things. It doesn't have to be an H2 necessarily. And then there's a sulfur version of that as well called a thiol, which is SH. These compounds are responsible for a lot of the really strong smells that we experience. Amines also, between these two categories, those are a lot of the what you consider bad smells. Everything from like decaying flesh to you know, poop and farts to cheeses to oniony, like garlic type flavors. All that stuff fits in these categories as generally amines and thiols, because of how those functional groups interact with our receptors, our smell and taste receptors. Okay, so now we're going to look at a list of a bunch of, you all right? We're going to look at a list of a bunch of groups. This is probably the toughest part. These all look really similar. They're all based on this C double bond to oxygen. And rather than being defined by just that piece, they're also defined by what else is attached. So we'll start with what's called an aldehyde. So an aldehyde is a carbon double bond to oxygen that has a hydrogen on one side. And these are found in a lot of different situations, such as if we put an aromatic on that aldehyde like this, that's benzaldehyde. That's kind of the sweet, like almond flavor that you might experience. Not so much it is in almonds. It is naturally occurring in almonds, but it's also used as kind of a artificial, like if you have an almond hand cream or something, that smell, that sweet almond smell is that aldehyde molecule. There was a time when synthetic aldehydes were really, really popular in perfumery. So if you know, if you ever like look at different perfumes and how they're described, sometimes they'll be described as aldehydic. And there was a time when that was really popular in the earlier 20th century. Some of those kind of old-fashioned perfumes that people aren't as popular anymore. What?
Old lady smell.
Yes, exactly. Yeah, yeah. So like those kind of like, what are some? I'm trying to think of like Shalimar is one of them. Is that? I don't know that one. Yeah. Yeah. And Chanel No. 5 is another one. I don't know that one. You may just be making stuff up. I don't know. No. But no, anyway, so that's these aldehyde molecules have these kinds of smells. Okay, so very similar to aldehydes are the ketones, which again starts with that C double bond oxygen, but now they're going to have carbons on either side. So a very similar molecule to the aldehydes, you can't just look at that, look for the carbon double bond to oxygen. You also have to look around it and make sure that there's carbon on both sides to call it a ketone. Ketones are also important in things like flavorings and smells. It's a relatively large molecule, so I don't want to put it on here, but we can look at it. Any like biological molecules that end in -one are usually ketones. So hormones of all those different types, if you kind of think about some of them, they end in -one. They are ketone functional groups. Let's see, what's an example they give here? This is a little bit smaller. We can draw this one. This is carvone, which is a spearmint flavor, spearmint oil. That's a ketone. All right, some other types now. Carboxylic acids. These are the traditional organic acids. So anything that's acid but also an organic compound would fall in this category. That's going to have that C double bond oxygen and then an OH. So something like this, which is acetic acid or vinegar. When it's 5% solution, it's vinegar. I was buying vinegar the other day, and I noticed that the vinegar I was buying didn't say vinegar exactly. It said vinegar style. Have you ever seen that? If you look at the label closely, you might see that sometimes. Turns out that for something to actually be called true vinegar, it has to be fermented. It has to start as wine and then get fermented into vinegar. The wine gets oxidized into vinegar through a bacterial action. And then it's distilled, so it's like purified. It is still pure acetic acid, but it's distilled and purified. But another way to make vinegar is to take pure acetic acid and make a 5% solution, which is the exact same thing as distilled white vinegar. But because it hasn't actually come from fermentation, you can't call it vinegar, so you have to call it vinegar style. But it's the same thing. All right, and then related to those are what we call the esters. These are more kind of flavor and aroma type molecules. And that's where it's kind of like an acid, but instead of an OH, it's an O and then something else, some other carbon stuff attached there. And that's an important, let's see, let me find a good example of that one. I had one here, there we go. Okay, so a lot of plant odors and flavors are esters. Things like this one. This is pentyl ethanoate, which is the banana flavor, banana smell. In organic chemistry, if you take a class, you'll usually do a lab where you make these esters. You start with these really foul-smelling carboxylic acids, and you react them and form these esters, and suddenly they become all these nice fruity, minty kind of flavors. So that's kind of a fun lab to do. And then we talked about amines. If we replace that N with a D, we have amide. Which again is a C double bond O and then with a nitrogen attached. And these are really important because this is how all proteins are built. Amino acids are an amine and an acid. And when they come together, they form an amide. So an amide bond is sometimes known as a peptide. And that's how amino acids link together to form proteins. So this is what we're all built from. And things like, if we're built from something, chances are it also reacts with us. So this molecule, which is an amide, see the C double bond O with an N, is acetaminophen or Tylenol. Aspartame, the artificial sweetener that's in Diet Coke or the blue packet version of it, that is also an amide. It's a link between two amino acids. All right, do we get them all? Oh, we missed one, sorry. So the last one is not a C double bond to oxygen. It's called an ether. And that's when you have an oxygen with two carbons between on either side. And those are known as ethers. Notice that it doesn't have the carbon double bond oxygen. So if one of those carbons was double bond to oxygen, it would be an ester. If it's not, it's an ether. That's an example of an ether. That's diethyl ether, which is sometimes just called ether. It used to be used as an anesthetic. You can inhale it, and it kind of knocks you out. They don't use it so much anymore because it's really dangerous. It's super flammable. So like operating rooms would explode all the time. So we use less flammable anesthetics now. It also is really nasty to come off of. If you're ever anesthetized with ether, when you come out, there's all kinds of, it's like having a really horrible hangover or something like that. So if somebody ever says, do you want to do some ether? Just be like, no, they don't want to do that. Ask for some better drugs. All right, and that is all the chemistry. So how would we use something like this? We would use this. You don't have to memorize this whole list. But what you should be able to do is take a list like this and use it to identify functional groups in a molecule. So let's try that. Let me go to a nice big molecule here. And let's identify the types of functional groups that are in here. So take a look at your lists and your notes. This is aspirin. So another painkiller. Can you find the functional groups in aspirin? So how many of the functional groups from the chart can you pick out in that molecule, and what are they? Not an aldehyde, but close. It's a different type of functional group. What? Yeah, we've got a carboxylic acid here. Where do you see an ester? Right. So right here we've got an ester. Anything else? Yeah, there's an aromatic group here too. Yep. So that's the functional groups. All right, let's take a look at another one. I should say what this is too. This is aspirin, which is acetyl salicylic acid or salicylate. This one goes like this. This is melatonin, which is a chemical that regulates biological cycles. Like, so you know when it's nighttime and daytime and when you're supposed to sleep, that kind of thing. So what kind of functional groups can you find here? Yep, there's another aromatic ring here, benzene ring. We'll find like 4 more. Yeah, where? Kind of like lower right? Yeah. So this one here is an amide or amide. Right, there's an amine also. So that, even though they look the same, NH and NH, because one is next to the carbon double bond oxygen, that's a different type of a functional group. What else do you see here? There's an alkene, yep. The double bond in there. One more. Yep, right up at the top is an ether. So it's a oxygen with a carbon on either side. So when you're looking to identify these, really what you're looking for is anything other than carbon-carbon single bonds, carbon-hydrogen single bonds. So if you see any double, triple bonds, if you see any non-carbon atoms like nitrogen, oxygen, sulfur, that kind of stuff, that's what gives your molecule its functionality. That's why we call that a functional group. All right, so that's what you need. The reason we kind of stuck this in, when I met with some representatives from some of the health careers programs last year. We meet periodically and we try to figure out like how we can make this class better and more relevant for people going into health careers. And they said over and over that functional groups was a big part of it, because when you go into those careers and you take classes like pharmacology or materials, health materials, things like that, they'll often be grouped around these ideas of functional groups, and to be able to identify those. Now in those classes, you'd have to memorize all this stuff and know it all, but at least get the sense of how you can identify and classify molecules based on their functional group. And then the next step would be learning how those functional groups interact with the body or with other things. That's going to control a lot of how they work. All right, so that's all the new stuff. Questions about this? Yeah. Yes. But again, you don't have to memorize all these. I would give you a table, and you would have to kind of do what we just did, identify the functional groups.
Oh, so it's like a table.
Yeah. All right.